Thanks. So, in the 13 minutes I have you for at the end of the conference, I'm going to try to explain some of the ways me and my collaborators have been thinking about modeling magnetization, specifically in the magnetospheres of magnetars. So, I have the privilege of giving the last talk, which means I can skip a lot of intro. We've already heard about why magnetars are interesting. We've heard about what regime they're in. So for these 13 minutes, we're going to think of them as basically laboratories for extreme plasma physics. And just worry about the physical regime we want to be in for the modeling. So the plasma is a paired plasma. It's highly magnetized, as we've heard. There's a lot of energy magnetic field, maybe ultra-strong magnetic fields. We're going to think about resistive MHD, so we care about the conductivity. So in the language of resistive MHD, the plasma has a very large Lundquist number, much beyond the critical value. So you should be in the plasmoid regime. These objects are slowly rotating. This doesn't matter here, so we're going to consider them as stationary. And as well, their fields are approximately dipolar. We saw a little bit about Koshik there, where they can be twists in different objects and different perturbations, which we'll talk about in a moment. And then, of course, we've heard about strong field QED effects, strong cooling. We won't be considering that, but they can be important. And then, less importantly, there's some small, jar effects as they're compact objects. I'm going to give a rough outline of basically how we model these generally. There's basically three groups of models. There's the force-free models, which we heard a little bit about. Here you neglect the plasma up until the fact you consider there to be enough to be supplying a current, but it's not dynamically important. And this is really nice because you basically have infinite sigma, and it's great for non-dissipative regions, which is pretty accurate for these magnetospheres, but it struggles when it comes to dissipation. You don't know how the energy is dumped into the plasma, so you're missing out a bit there. And then the next class with a little bit more sophistication would be the fluid models. There you make a sacrifice because now you have a collisional fluid, which is not the best model because these are collisionless plasmas, but you do gain some sophistication. You can now model dissipation self-consistently, but there's also some pains. MHD doesn't like high sigma, which we want. This is just a numeric artifact, but something we have to fight. As well, if you include resistivity, you can also self-consistently model any kind of resistive effects, which is also nice. And then, of course, we can come to the best choice, which is particle and cell. And this is nice because we include the plasma, it's a collisionless, you get all the kinetic effects, which you smear out in a fluid model. But with all that great power in the model, you do get expense. You have all these scales, you have to separate them properly, you have to resolve them, you have to have a lot of particles. This becomes very expensive and difficult. But there's also obviously a lot of merit there. We'll be talking about the fluid models for these next 10 minutes. And I'm basically going to try to break this into two parts. We're going to consider a local simulation and a global simulation. So we're going to ask ourselves simple questions for both. So for the local simulation, we're going to think about how do the internal motions of a neutron star or a magnetar, how does this drive current instabilities? And this is a little difficult because there's three things you really care about here. There's internal motion, which can be quite complicated by itself. There's the actual global structure of the magnetosphere, which isn't obvious. And then there's all the way down to the kinetic scales where the current instabilities live. So you have to break this down to really tackle the problem. So what we're going to do is basically zoom in and simplify this. We're going to remove the global geometry by basically just considering some weakly twisted flux tube, straightening it out into a cylinder, removing the global geometry. We're going to remove the interior physics by just considering some perturbation that's localized, maybe some fault or some kind of extreme event. And we're going to consider an extreme case where there's actually a reversal in the twist. This is nice because we can model this in 2D, roughly for a strong guide field. The reconnection won't be that different. So when we go to 3D, we have some good idea what to expect. This whole thing can be done with force-free equilibrium. You can think of the strong guide field as basically the dipolar field along the flux bundle. And the twist, it just runs some slow twist from the star. We're going to do 2D resistive MHD simulation, so full self-consistent resistivity. But there we can use AMR to really resolve those small resistive scales. Life isn't so easy in 3D. I won't have time to talk about this, but feel free to ask about why we do ideal MHD there. So here I have a little movie showing exactly this setup. So we have a flux tube which is twisted in two different directions. You see the perturbation there in the corner. That's going to excite reconnection because the interior half and exterior half, they have opposite signs of current, or total current, so they want to repel each other. And when you basically prick a little hole in that balance, the exterior one will push it in. This is the current out of the plane, normalized by the RMS value, and this is the temperature, and it's uniform to start. So I let this go, you'll see, you perturb it, it forms a current sheet, quickly reconnects, generating a bunch of small-scale current, feeding the plasma in the process. You open this tube with a bunch of structure. I'll let it play one more time. And it just shreds the interior of the tube. So what's actually happening here is we drive reconnection at a single X point, which if you're familiar with strong guide field reconnection isn't that weird. Typically for very strong guide fields, for example, we had 5 here, you'd only get maybe 1 or 2 X points typically. And here you can see basically how small these strong currents are. So this is showing the area occupied by different values of the current normalized to some equilibrium value. You can see reconnection times, which are in the white, before is red and after is in blue. During reconnection, you get huge currents, 100 times the initial maximum, but they occupy a very small amount of area. So these are very localized small currents, which would be great for particle acceleration. And in the whole process, you can see here's some azimuthally average magnetic field components. The B5, so the twist to the tube, you shred the entire interior, it goes to 0 nearly in the middle, and also the guide field becomes constant there since it no longer needs to be balancing any B5. So in doing so, this is a great way to accelerate particles. If you're familiar with this kind of idea of these twisted flux tubes, it's just similar to the kinking idea, but more localized to reconnection. Okay, so that was a local simulation. But we also can do global simulations of MHD that address problems. So we're going to ask yourself another simple question, which is how do fast waves steepen in a magnetosphere? So if you have been here for the last 4 days, you can probably guess what I'm going to talk about, as we've heard like 3 talks about it. So I'll keep it brief. Monster shocks are basically a mechanism where fast waves steepen, so you can launch different waves due to internal stresses of a variety of kinds. They can interact, produce fast waves, or it can generate fast waves from the start. And basically, it's a very simple idea. If the fast wave is polarized such that it is opposite of the background, you can have E approach B quite easily because the fast wave drops off slower than the background. So the relative amplitude grows. And these are very strong shocks. The Lorentz factor of the upstream can peak at a value which grows linearly to magnetization. So for these highly magnetized magnetospheres, that's a huge value. And there's been lots of work done on this. It started off 1D simulations by Chen, and we heard a little bit about these simulations by Arno and Amir as well, with huge scale separation in 1D. And then recently there was actually a 2D global kinetic simulation by Dominic Bernardi, and he found this linear scaling. You can see this is the structure of the shock as it spreads out in latitude. There's also been 2D global MHD simulations with dynamical spacetime, for neutron star mergers and black hole neutron star mergers, where they see these kind of structures as well. But no one's really done it just in a pure dipole and MHD at large magnetizations, because it's a bit of a pain. So here I have a bunch of panels. On the left are cuts along the equator. The top are magnetic field and electric field components, and you'll see the wave launch from the star. E will approach B, and you'll form a very strong, very large, radially inward forward velocity on the bottom panel. Here's just showing the wave propagating electric field component along with the mesh refinement following it. Here's the flux function contours along with the Lorentz factor. So you'll see the upstream become very large Lorentz factors. And then here is the temperature. The background is 0 temperature, infinitely cool. And you'll see heating behind the wave. So I let that play. See the wave is launched. E approaches B. Develop a huge Lorentz factor, spreads out an angle, and heats the downstream. And that doesn't seem too crazy. It's pretty simple. And things work basically as you expect they should. This isn't surprising. This all fits great to analytics, which was derived in the MHD framework. Here I have linear scalings with the expected values for the maximum Lorentz factor on the equator, with the slopes of the fit on the top and then the expected slopes below them, and they all agree very well. So we have this nice MHD tool where we can model this monster shock at very large magnetizations, but we don't expect these magnetospheres to be so simple. We can do more interesting things than just a pure fast wave. And since we now trust it, so things like alpha waves and other choices. So I'm going to show you a bit of an extreme example, but in an experiment where we have a very strong perturbation. Basically, we're going to wrinkle the dipolar field lines with a very large delta B over B, and want to see what happens to the fast wave. And there's other choices as well. You know, one serious interest is how fast the steepening can compete with dissipation, but this is quite difficult in 2D. The full wave interactions require 3D, so we don't do that. And what you see is actually these wrinkles fragment your wave into localized zones, with enhanced Lorentz factor. You actually get significantly larger Lorentz factors going from about 8 to about 30 in this example. You can see, if you look at top right, this is basically just a chunk of the normal monster shock, but now it's fragmented. In the middle, we get a bit of a weird structure where the flow is actually converging to a point almost, at a very large Lorentz factor as well. But this is roughly still the same monster shock mechanism. E is approaching B, a larger Lorentz factor. Additionally, you can see here this plot, which is a little hard to read on the screen on the left, where we're plotting the maximal Lorentz factor in each theta bin as a function of time. And you can see basically these strong Lorentz factor regions kind of blink in and out of time, moving around in the magnetospheres. There's not this constant growing wavefront. And this is a bit of a problem in terms of the radio emissions. We heard Arno talk about this a little bit, and this is obviously something we cannot model with MHD. It's a purely kinetic effect. I can't model with a maser. But you can comment on the fact that for the radio to escape, it needs to surf the wave. So if the wave is fragmenting when it hits other modes, if they're large enough, this could be an issue for the escape. Okay, and there I just want to make some concluding remarks about basically how things are going in this area. So neutron stars, magnetospheres are still a significant numerical challenge, both for MHD and PIC. MHD, we have sigma issues. PIC, you have scale separation issues. Things are expensive and difficult. They're getting better. Going forward, we'll still have to use a smart mix of local and global simulations where appropriate. But things are getting better, particularly with GPU acceleration for both MHD and PIC. High resolution 3D simulations are becoming viable in both. So we can really start probing some better stuff. And then I wanted to highlight some of the efforts being taken at our group at CITA to improve these models. So we heard Lorenzo talk about this non-uniform resistivity model along with Felicia for charge derivation and X points. We've also been looking at using test particles to retrieve particle spectrums from reconnection simulations in MHD. Alicia talked about cooling. And then also, I had mentioned how force free is really nice in non-dissipative zones, which makes one ask, what if I can do both? What if I can do dissipation and the force free? Koshik mentions a little bit. That was particularly for fluorine. That's not actual full coupling. We're talking about here an actual coupling of two models through a self-consistent evolution of both and coupling them through a resistive current on both sides. So it's actually force-free non-dissipative zones. I don't have time to talk about that, but I'm happy to chat. That's it for me. Thanks.
Thank you. Great.
I'll myself. Have it.
Any questions? Oh, great. Wonderful.
Hello. I was wondering about the filamenting or the focusing of the field. So it's just a magnetic field, it's not an electromagnetic wave?
Are you talking about the monster shock specifically? Or?
Yeah.
Yeah. So what we do here is we start with basically the standing wave, which are wiggles. So they are waves in a magnetosphere.
And then do you want to comment on why it's filamenting? Is there density perturbations there as well, or is it just the field?
No. So basically what happens is the wiggles are polarized such that they're in the same plane as the fast wave. So you're going to have regions where they constructively and destructively interfere with each other, which will change where they shock and basically the whole evolution of the wave.
Okay, thank you. Any other questions from anyone? Okay, I guess everybody's tired. All right, so in that case, let us think. Oh, there is, okay. Anatoly came. So organizers of the conference are coming to the rescue. So where is Sasha? Sasha is next. Asking next question.
Could you explain more on how you're going to couple the MHD with force-free?
Yeah, so what we do there is there's this force-free resistive scheme where instead of evolving a normal fully time-dependent force-free current, you evolve what looks like an Ohm's law if you replace the velocity of E cross B drift. And this works pretty well for force-free, and you basically, instead of instantly dampening your violations, you dampen them on resistive timescales. So what you can do is have some condition to couple between the full MHD current and the force-free current. And in regimes where you want to be force-free, you evolve electromagnetic fields according to the force-free equations, and the fluids field of fields, but the fields are not field of fluids. And you can smoothly interpolate between the two currents in regions where you want to enter the MHD. And there you'll have the full resistive MHD current.
So You don't need to do anything special about velocity of the fluid along the field lines when you switch to force-free.
No, you don't. That's the nice part. You fully self-consistently evolve the fluid feeling the fields. The fields just don't feel the fluid.
Got it. Thank you.
I was forced by the friendly organizer. So can you explain a bit where do you think this large amplitude perturbation may come from?
Yeah, so this is a bit of an extreme case to see basically what we can do. But we don't expect this to be just a clean magnetosphere. These, if you're going to launch a fast wave, it's probably either launched itself or through some interaction between alpha and waves. You expect there to be some other activity in the magnetosphere, so you expect other modes. This is a pretty large amplitude one, but if this is happening far from the star, it's not unreasonable that, for example, some kind of wave is growing large compared to the background. Sorry, I didn't quite hear that.
You need to put as much energy into this perturbation as you're putting in the escaping of a mass wave.
Mm-hmm.
So very large.
Yeah.
More than what this actually has.
Your nonlinear radius is large, then you don't need to do that.
I've asked him enough questions already.
You launched this wave from like a large fraction of closed magnetic field lines. Did you try to launch it along like a very, not a very, but a reasonably thin bundle of magnetic field lines and look what?
That can easily be done. It's just, what do you expect to be different? That's going to just be one chunk of the wavefront.
Oh, but I mean, so just there will be like a clear asymmetry, I think.
Symmetry, what do you mean?
No, I mean, so just the front which goes closer to the dipolar axis will propagate differently than the front which moves sort of along magnetic field lines at large theta from the dipolar axis.
Are you talking about the fast wave launch from the start?
Yeah.
Oh. So you're
Just a thin tube and load this perturbation and maybe just you will get just some qualitatively different behavior. I don't know.
Okay. I don't see why it would change, but yeah, this could be easily tested. Yeah.
Thanks.
Okay. Thank you. If there are no other questions, but let me check. Are there any questions? Okay. Well, in that case, let us thank Michael and